Hello everyone. So I have picked up this problem from Pathfinder Electrostat Build Up Your Understanding section, and the main motive behind picking up this problem is not the difficulty level, because I guess it's not conceptually very tough problem, but the thing is the method is a bit interesting. We'll use the vector method to solve this problem, a bit interesting than the conventional method. Okay, so first read out the problem once, then we'll come into the solution. The problem states that a charged particle A is fixed at the base of a uniform slope of inclination alpha. Another charged particle B is placed on the slope at an angular position beta from the line of greatest slope. So you can imagine the line of greatest slope. It has also been shown on the figure. Of the first particle, coefficient of friction between the particle B and the slope is mu, and mu is given less than tan alpha. This has also a very good significance. I'll explain it in the solution, right? That why mu is less than tan alpha is given, and otherwise what would have been the result of our problem. For the particle at B to stay in equilibrium, what could be the maximum value of the angle beta, right? So as I said, I'll solve this with the vector method. Some of you might know this method earlier, but yeah, you will enjoy the solution, that much I can say. So let's draw the diagram here. I'm drawing the inclined plane surface here, showing as a vertical plane. So here G will be vertically downward, right? And as we are drawing the inclined plane surface, it will have a component of G sin alpha along the inclined plane and G cos alpha perpendicular to the inclined plane, right? So in my drawn plane, I can show G sin alpha as vertically downward acceleration, right? Because you can imagine, right, the plane is, I'm just projecting that inclined plane as if it is a vertical plane, and here A is fixed. Whatever be the charge, I'm not writing this because we will not need that. This is the line of greatest slope, and let's say here is B, another charged particle, which is at an angle of beta from the line of greatest slope, right? So let us first determine what are the forces acting on B. The first one is mg sin alpha downward. If mass of B is m, is it mentioned? No, so we're just assuming that the mass of B is m, right? Let me write it here. Let mass of B equals to m. And what about mg sin alpha? Mg sin alpha is constant by magnitude and direction both, so it's a constant force. And then comes friction. What is the maximum value of friction? Mu into normal reaction. And you can imagine that normal reaction is nothing but mg cos alpha in this case, as here g cos alpha is the acceleration perpendicular to the plane, and the normal reaction will balance B to stay on the plane. So if maximum value of friction is mu mg cos alpha, this is the maximum value. And as we are dealing in the critical case for maximum value of angle beta, you can understand that friction will act the limiting friction, that is mu mg cos alpha, but we are not sure about the direction. So friction is the force whose magnitude we know, that mu mg cos alpha. In this particular case, its maximum value, we are assuming that friction is at its maximum value, but we are still not sure about the direction. So let me write it down here. Magnitude fixed, but direction we are not sure yet. And for mg sin alpha is magnitude and direction both fixed. So this is the one force, this one is the second force, and there is another electrostatic force if we assume that A and B both are positive by convention. So we'll have electrostatic repulsion force along this direction, line joining A and B. Let's denote this by Fe. the electrostatic force. I am not interested in its magnitude of assuming K, Q1, Q2 and R square, all these stuffs. Let's not make these things complex. Keep it simple. Fe, the electrostatic force acting along the line joining the two particles. And so this one is the third force, right? So we will deal with these three forces, and B is under equilibrium acting these three forces. So let's write the vector equation, that friction plus electrostatic force plus, let's say F1 is mg sin alpha force. We're assuming this, its magnitude I should write like this. This force I'm writing as F1. Okay, so these three forces will sum up to null vector, not zero. Be technically correct. Okay, as Fe equals to friction plus F1. I'll tell you what's the purpose of writing like this. Sorry, minus will be there. So F1 is a constant force by magnitude and direction. So minus F1, you can write this as minus F plus minus F1. So this is also a constant force by magnitude and direction both. But this is only constant by magnitude, right? We have already discussed earlier. So if we add vectorially this minus F and minus F1, we will get Fe. So I'll draw the vector diagram here. Let's say this one is the minus F1, whose magnitude is nothing but the length of this vector, which is mg sin alpha, as we discussed. And friction will have variable direction but constant by magnitude. So let's say it's something like this. This is minus F. Okay, so what we are doing by triangle law, we can add the two vectors by coinciding the tail of one vector with another one's head. So we are using this fact here. But minus F can be on this circle, the tip of minus F can be on this circle anywhere. You can imagine, right, that this could be minus F, this could be also minus F, this could be also minus F, because it moves on a circle of radius equals to mu mg cos alpha, because magnitude is fixed, the direction is not fixed. But as we are finding the maximum angle, maximum of beta, I will also relate beta with this figure again, just wait. But as we are dealing with the maximum angle, so let me show you the maximum case. So by vector addition, we will get this one as Fe. So I am claiming that this angle will be beta maximum when this is the tangent, when Fe is tangent to minus F, the circle of minus F, the circle whose radius vector is minus F. Why so? Because you can imagine if minus F is something like this, then also you will get angle less than beta. If minus F is somewhere here, then also you will get angle less than beta maximum. So I'm not going to mathematically prove this, but it's evident from the figure that the maximum of beta will occur when Fe will be tangent to the circle I have drawn, right? So now, yes, the angle is maximum, but why I'm saying that this is beta max, let's move on to the diagram of the question. So yeah, here come, this is Fe direction, right? And this is the direction of Fe, and this is the direction of minus F1, that is minus of mg sin alpha. And this angle by geometry you can see is also beta if this angle is beta. So the angle between minus F1 vector and Fe vector is nothing but beta. In here also I have shown that minus F1 and Fe, these two vectors subtend angle beta, and in critical case I have denoted this as beta max. So this length is mg sin alpha, and this length I have forgot to show, that this will be mu mg cos alpha, right? So from triangle, using trigonometry, you can easily write that sine of beta max will be mu mg cos alpha upon mg sin alpha. So we'll get mu cot alpha, sorry. So beta max will be mu sin inverse mu cot alpha. So this is our answer for this question. And as I said, there is one significance of why mu is less than tan alpha is given here, that mu is less than tan alpha. This is just because here if you see the radius of this circle is mu mg cos alpha. If mu is less than tan alpha, then mu mg cos alpha will be less than mg sin alpha. So the circle, the tip of minus f when revolving on this circle will cut in some point here at minus f1 vector. But if mu would have been greater than cot alpha, sorry, mu would have been greater than tan alpha, then minus f, that is mu mg cos alpha, would have been greater than mg sin alpha. In that case, let me show you what would have been the diagram. In that case, it would have been like this one, minus f1, and this one was the circle. It's a very bad drawing, but please cope with this. This one would have been minus f. So in that case, you can imagine that the radius would have been greater than mg sin alpha. And for maximum beta, beta is what? Minus f1 and fe, the resultant of these two, the angle between these two vectors. So in that case, this would have been the friction, sorry, this would have been the minus f and this would have been fe, and its resultant would have been in this way, fe. So fe and minus f1, these two would have been subtend 180 degree angle. So 180 degree would have been our answer in that case, but as it is mentioned mu cot alpha. In fact, here also you can satisfy the domain, right? That mu cot alpha, if it would have been, if it was not given that mu is less than tan alpha, then mu cot alpha would not lie in the domain of sine inverse. So anyway, you got the justification of why it is given that mu less than tan alpha. And I hope this method is a bit beautiful and you have liked this, and you can use this in many problems. Like we very frequently use this method in center of mass, frame and collision problems. So, and yeah, I think riverboat, you all have come across riverboat problems. We find the shortest distance, shortest time. There also you can use this method. If required, I will show you in some later video. So okay, that's all for today, and we'll come up with some beautiful problems later on. Bye.